Hey, I'm Laren. This is Knife Steel Nerds. We are going to talk about some nickel alloyed steels. So, surprisingly, there are not as many nickel steels as you might think, but there are a few key ones that are pretty common, especially like 15 and 20, 8670, L6 steel. For example, 15 and 20 is used in a lot of Damascus, usually along with something like 1084. The main reason to add nickel to steel is the increase in toughness. So how does nickel increase toughness? That might take too long to explain for this video. I will include a link in the description to what nickel does to steel, but I have to explain what dislocations are, what the ductile to brittle transition temperature is, what cross-slip means, and I think people are just going to get bogged down. So instead, we'll just talk about the results of a bunch of experiments I did with nickel steels, including 15 and 20. So I did a bunch of new experiments on 15 and 20. I got it from New Jersey Steel Baron. They buy it from a company in Germany called Buderus. So 15 and 20, it's a product originally introduced by Udahome, which has the same parent company as Buderus, but they are different steel companies, and so the properties might be a little bit different. But in part to mitigate that, and also because this steel is very commonly forged, I did a series of, we'll call them thermal cycles to the steel to get it to a consistent condition. So first I did a forging simulation at 2000 degrees Fahrenheit for 30 minutes, and I air-cooled. Then I normalized at 1550 for 10 minutes and air-cooled, and then I annealed by holding at 1385 Fahrenheit for 30 minutes, and then cooled at 300 degrees per hour down to 1100 degrees, and then I just let it cool in the furnace. The cooling rate below 1100 degrees doesn't really matter because the transformation has already happened. So in the annealed state, the steel was nice and soft, slightly harder than it came from the mill, but it also probably has a finer microstructure, which I think is probably a good thing. So next, I heat treated the steel. I measured the hardness after tempering at different temperatures, and I also measured the toughness of the steel so we can see, how much toughness do we get from these nickel additions. So I tempered between 300 and 450 degrees after austenitizing at 1475 for 10 minutes and quenching in Parks 50 oil. And the steel gets nice and hard as quenched, so I got a little over 66 Rockwell. And it's still over 63 after tempering at 300. It goes down to about 58 when tempering at 450. So a decent range of hardness. Now the toughness, I saw a huge increase in toughness by going from 300 degree temper to 350. So 300 degree temper was just under 10 foot-pounds. Going to 350 degrees got to almost 50, and then 400 degree temper bumped it up a little bit. And then tempering at 450, there was again a drop in toughness. This is from a phenomena called tempered martensite embrittlement. So this is somewhat unexpected because usually the softer steel is, the tougher it is. So we temper it hotter, it gets softer, and we expect the toughness to continue to rise. But instead, it went down by tempering at 450. So tempered martensite embrittlement, that is when you get coarse carbide particles that form when tempering at those temperatures. So when you temper at low temperatures, the martensite softens by precipitating carbon out as little tiny carbides. And as you temper hotter and hotter, those carbides get larger and larger. When they get coarse enough, they actually start to decrease your toughness, even though the hardness has also been reduced. Then when you continue on and tempering up to hotter temperatures like 600, 700 degrees, the toughness starts to go up again because the coarse carbide particles aren't affecting things as much as just softening your overall steel. We've also seen this phenomena with other steels at similar temperatures, like 5160 we also saw a drop by tempering at 450 degrees. And 5160 also saw a large increase in toughness by tempering hotter than 300. Even with 5160, we had to temper at 375 before we saw the big jump in toughness. Some steels behave differently. Some steels you just temper lower and the toughness gradually decreases. But with these high toughness steels like 5160 and 15 and 20, they seem to have this huge jump above some minimum temperature. So that's something to keep in mind if this is a steel you will be heat treating. Also, some steels don't see tempered martensite embrittlement until higher temperatures, like 80 CRV2 and 26C3. Both of them you could temper all the way up to 500 degrees, 450 degrees, and they were still tough. And it wasn't until you tempered hotter that they would see the drop from tempered martensite embrittlement. So that can change based on steel. It might also change even some from heat treatment, like maybe a different austenitizing temperature can shift the position of where the tempered martensite embrittlement starts. I'm not sure. I haven't looked into that very much, haven't seen it really in the literature. Would be an interesting thing to look at, but for our purposes, 15 and 20, really high toughness, especially when you temper between 350 and 400 degrees. And this thermal cycling procedure that I did seemed to work really well. Now, 8670 is somewhat more complicated. In early studies of 8670 with some steel that came from Alpha Knife Supply, heat treated by knife maker Warren Kryko, and then I machined the specimens and tested them, we got really high toughness, close to that of the 15 and 20 that we just discussed. But then I did another study on 8670 along with Pop's Knife Supply with their 8670, which comes from a different source, though neither company says which steel company produced the original steel. And the toughness was significantly lower than our original Alpha Knife Supply steel. And so because we were worried that this was some kind of fluke, Warren and I heat treated and machined some new coupons with a range of tempering temperatures to see, what is the trend here? Why is this steel so much tougher? And we got a similar hardness curve to what we had with 15 and 20. And again, we saw a rapid increase in toughness by tempering at 350 to 400 instead of 300. So again, the trends are holding. We didn't go out to 450 to see if tempered martensite embrittlement also is seen at 450 degrees. But overall, the steel is looking pretty similar to the 15 and 20, even though the 8670 does have lower nickel than 15 and 20, about half as much. So with the Pops material, one thing I noticed with the coupons that they had sent me, because they heat treated and machined them themselves and then I tested them, is that the way that they had ground the specimens, the grind lines were in an unfavorable orientation, meaning when the crack forms in the specimen as we're breaking it, it's forming along those grind lines, which drops the toughness. So one thing I did was heat treat and machine my own specimen out of the same steel, and indeed the toughness did go up significantly, though not to the heights of the Alpha Knife Supply material. So I did yet another study on this material for this video, where I did my same thermal cycling procedure that was on the previous 15 and 20. This would allow us to eliminate any differences in the steel in terms of prior microstructure. So I eliminate the carbide structure of the steel as it comes from Pops, and I instead cycle it to give it a nice fine annealed microstructure that I know works very well, then heat treat it and test it. And it did get slightly tougher than the one that I had originally ground, but not so much to write home about. Maybe even if we did more specimens from both, they would be even closer together. Can't say for sure. But it's still not reaching the level of the Alpha Knife Supply material. So 8670, a little bit mysterious to me. Why is there such a big difference between these two sources of the steel? Because the Alpha Knife Supply material is off the charts tough, and the Pops material is very good, but not as stellar as the Alpha Knife Supply material. I still don't know the answer to that. Maybe we'll be able to figure it out with more investigation, but for now, this is what we know. Another steel we looked at was L6. Again, Warren, who has been a superstar with heat treating steel for these toughness tests, he looked at some L6 that he had gotten from New Jersey Steel Baron years ago. And we're not sure the ultimate source of this L6 either, though Warren did know that it was not the molybdenum version of L6. There's two major versions of L6. One comes from Carpenter and Latrobe without moly, and one comes from Crucible with moly. And this was the moly-free version. And the toughness of the L6 was very good, but not as high as the Alpha Knife Supply 8670 or the 15 and 20 we just talked about. And some knife makers were disappointed in this or questioning the result. L6 is a nickel steel. Why isn't it up in the 40, 50 foot-pound range? And one thing I said in response is that from some of the steel companies, they also don't rate the toughness of L6 as being all that high. So I have data from both Crucible and Latrobe with different toughness tests than I use. So the numbers you'll see on these charts are much different than my test. You can't compare different toughness tests to each other. But these are two different companies, two different types of toughness tests, and they show L6 as being significantly less tough than 3V, where if it was testing in the 40 to 50 foot-pound range for my steel, it would test at least as well as 3V, but it is not what we saw from these two companies. So in a way, the L6 is meeting expectations if we look at old steel company data, but it's also not meeting expectations if we think about other nickel steels like 15 and 20. So I also did a new study on this steel because one of the criticisms of Warren's original heat treatment is that he used an austenitizing temperature of 1550. And the Crucible datasheet says use 1500 to 1550. The Latrobe datasheet says use 1450 to 1500. The ASM Heat Treaters Guide says use 1450 to 1550. And I know that 1500 works very well for 8670, which is also a chromium-containing nickel alloyed steel. So I thought, okay, I will redo this experiment but use 1500. I will also do my thermal cycling procedure to see if it's a prior microstructure issue. So I did my same range of thermal cycling with the forging simulation and the normalize and the anneal, and then I austenitized at the somewhat lower temperature of 1500, and ultimately the result was that I got about the same thing as Warren originally got with the 1550 austenitized and the as-received microstructure from the steel company. So why is the L6 less tough than 15 and 20 and 8670? I still do not know. If I get some other L6, maybe from a different source, like we get the Moly version, for example, I would be interested to see how that tested, if it does as well as 15 and 20. But for now, this is the result that we have. The L6 tests very well for toughness, but not stellar like the 15 and 20 did. Now, my heat treatment did result in a little bit higher hardness, probably because the annealed microstructure I developed thermal cycling was finer than from the factory. But that higher hardness was also offset by somewhat reduced toughness, which means that in the end it balanced out and they were about the same when it comes to hardness, toughness, balance. Another steel I tested is 4340. This one isn't used in knives that much because it only has 40 points of carbon, which limits its potential hardness. But it has almost 2% nickel, so I thought it would be interesting to throw in here. As quenched, so I austenitized at 1550 and quenched in Parks AAA, I got 59 Rockwell, and after tempering at 400 degrees, I got 54 Rockwell. And the toughness was even higher than the higher carbon steels, as we might expect, about 60 foot-pounds. And so this steel could be useful for certain applications, maybe axes or swords, or applications that don't need really high hardness, but need really, really high toughness. They cannot fail through chipping or breaking. So if we compare all those steels that we talked about, L6 and the POPS 8670, that's after I improved the machining and the heat treatment of the steel, they are kind of in the 20 to 30 foot-pound range at 60 Rockwell. The Alpha Knife Supply 8670 can get as high as 40 to 50 foot-pounds around 60 Rockwell, and 15 and 20 can be around 50 foot-pounds, even a little above 61 Rockwell. So 15 and 20 got the best hardness-toughness balance. The Alpha Knife Supply 8670 just a touch below. And so maybe the POPS 8670 isn't so much bad as it is just very good, while the Alpha Knife Supply version, for whatever reason, is very excellent. And we might say the same thing about the L6. It's very good, not bad, though compared to the 15 and 20, not as exciting as we might hope. So comparing these steels to others, the 15 and 20 8670, they are chart topping on my low alloy steel toughness hardness chart. The only steel that really approaches it is 5160, which has lower carbon, 60 points instead of 70 to 75 points of carbon. And just like we saw with 4340, the best way to ensure that a steel has high toughness is to have lower carbon. So if you can get 54 Rockwell with 40 points of carbon, that's probably going to give you higher toughness than tempering a high carbon steel down to that hardness. And so 15 and 20 and 8670, they seem to be able to make up for their little bit higher carbon than 5160 through the addition of nickel. So it does seem like nickel is having a positive effect on toughness. And for the 59 to 61 Rockwell range, these steels are the best there is, especially if you're a forging bladesmith looking for simple steels that are easy to forge. However, when it comes to high hardness, I've seen this trend with some bladesmiths in recent years, that they take something like 15-20 or 8670 and they temper it at a low temperature to try to get 63, 64 Rockwell, because they say, well, this is a high toughness steel, so I will temper it to a high hardness and get the benefit of high toughness and high hardness. However, as we saw with the tempering curves of 15-20 and 8670, when you tempered below 350 degrees, the toughness falls off a cliff. Now, the steel isn't like suddenly super chippy or break really easily, but it looks more similar to other steels. It's not these chart-topping toughness steels anymore. So I think once you go beyond about 61 Rockwell, it makes more sense to move to a higher carbon steel. And so I have some options here. So even 80 CRV2, you can temper it down to like 63.5 Rockwell and still maintain pretty good toughness. But you can also move up to 1% carbon steels like Crewforge V or 52-100, and they can be heat treated to 64 plus RC without their toughness really falling off. I have a separate article on how to heat treat 80 CRV2 and Crewforge V if you're interested in how to heat treat those to 64 Rockwell. I need to do an article on 52-100. I don't have anything on how to do high hardness heat treatments for it, but you can see that around 65 to 66, 52-100 looks great, but it does start to fall in toughness beyond about 66 or 66.5. And beyond that, it would make more sense to move to Apex Ultra, which is a low alloy steel for forging that I developed along with Tobias and Marco, which is designed for high wear resistance and high hardness for a low alloy forging steel. So if you want to go 65 plus Rockwell and you want wear resistance and good toughness, Apex Ultra is the way to go. Though it is more of an advanced steel. You have to know what you're doing to work with it, where 52-100 can be a little bit easier. Okay, so we talked about hardness and toughness. These nickel steels can be pretty good in that regard. But in terms of wear resistance and slicing edge retention is where they sort of fall down. Now, because these steels have about 70 points of carbon, they have little or no carbide remaining in the microstructure after heat treatment. Carbides are hard particles formed between carbon and a metal, and those hard particles are what give your steel wear resistance beyond just the hardness of the matrix. So you can have a steel which is only 50 Rockwell with lots of hard carbides that is more wear resistant than a steel which is 66 Rockwell which has no carbide. That's the effect that carbides can have. So these steels with almost no carbide in them are quite low when it comes to wear resistance and slicing edge retention. So this is a chart of my Catra slicing edge retention testing, where you can see that the very lowest steel on this chart is in fact 8670. It was only about 60 Rockwell, and it has very little carbide. So if you want more wear resistance, you need to move up to steels with more carbide and or at higher hardness. So again, Apex Ultra is a very good option for this. Other options with a little bit lower wear resistance would be things like 52-100 or Crewforge V. So again, these steels, 15-20, 8670, L6, they are not great for 62 plus Rockwell. They are not great for high edge retention, but they do have their place in that 59 to 61 Rockwell range with stellar toughness to go with it. Now, another steel I'm not really going to discuss is Z-Tuff and CD number 1. These steels also have 1.5% nickel, which makes them very interesting. There's very few high alloy air hardening steels with significant nickel additions, but I already have a separate video and article on those steels, so I recommend you go read that if you want to learn about high alloy steels with nickel additions. Another thing I want to discuss is why there are not more nickel steels. So, these nickel steels, they seem to be pretty great for properties. Why aren't we adding nickel for toughness to more steels? Well, there are a couple major reasons. One is that nickel reduces the temperature where steel transforms to austenite. Okay, this sounds like a very random thing. Why would this matter? That temperature is also called the critical temperature or the A1 temperature. And this is an issue because when you anneal steel, you heat it up to non-magnetic and you slow cool to soften it. It doesn't start transforming to the soft phases until it gets below the critical temperature. And when that critical temperature is very low, it becomes extremely difficult to anneal the steel at all. And if you can't anneal the steel, then it doesn't work well, especially in industrial settings. But even for your average knife maker, he's trying to slow cool steel and soften it to be able to drill and bandsaw cut and everything. And if you can't anneal it, then you don't want to work with it. So you're limited in nickel additions by this fact. Another issue with nickel is that it reduces the temperature where martensite forms. Martensite is the hard phase that we form during quenching. So we quench the steel in oil, it gets very hard, and that's what gives us our nice strength and edge retention properties in the steel. And when martensite formation occurs too low, you have retained austenite. So the austenite was the high temperature phase. If it did not transform to martensite, it is retained, and that soft austenite does not contribute to our hardness and strength and edge retention. This is commonly talked about when it comes to cold treatments and cryogenic treatments, which are more common with high alloy steels and stainless steels, though you can also do it with low alloy steels. And because steels like 15N20 and 8670 and L6 are pretty low in carbon and they don't have much other alloy, the nickel addition doesn't make too big of a difference. But if you're working with a stainless steel, for example, especially something like VanX or LC200N, where they already max out at 61 Rockwell, or a lot of stainless steels can't get any harder than about 63, 64, maybe 65 Rockwell. If you added a significant amount of nickel, that would further drop the hardness they can reach, because the nickel would stabilize your retained austenite and further lower the temperature at which martensite forms. So you can see that in this chart I pulled from some old literature data I found, where they looked at an M2 high-speed steel with 3% nickel. And adding the 3% nickel took the M2 from a 66 Rockwell steel down to a 63 Rockwell steel. Now, 3% nickel is more than you need to add, but you might imagine if we want our stainless steels to be able to hit that 64 Rockwell, and then we add 1.5% nickel to it, that might become a 62 Rockwell steel, which could be undesirable. Maybe there are certain cases where this could still work. We make sure we're not adding too much nickel. Maybe stick to 1.5% or 1% or 0.75%, I don't know. Especially for steels where we want high toughness. So I think this is an avenue worth exploring for certain steel designs, but given that we've known about the effect of nickel for 100 years and there aren't more steels coming out with it, it's probably not very likely that we're going to see many more. Okay, so to summarize, nickel is a great element for improving toughness. 15N20, 8670, and Z-Tuff in particular are the highest toughness steels I have tested, and each of those has a significant nickel addition. Of course, their toughness is also helped out by the fact that they are all 0.7% carbon steels and they have very little carbide, but they do have excellent properties in that 59 to 61 Rockwell range, maybe a touch harder, where you need really high toughness. Another thing I do want to talk about is heat treating with a forge. I do have a separate video on how to heat treat with a forge, but I do a very simple method for heat treating in a forge where you can heat to non-magnetic and no hotter and then quench straight away. So with nothing but a magnet, you know when the steel is ready to quench. And so what I do is I do a normal normalizing treatment, and then optionally you can add a grain refinement treatment where you heat it to non-magnetic and then air cool, and then nothing else. So just these 1 or 2 steps, normalize or normalize plus grain refinement. That's all you have to do. Then you heat to non-magnetic. Don't go any hotter. The main mistake people make is overheating. You can do all the thermal cycling in the world and have that grain super, super fine, but if you overheat it before quenching, it's going to have a coarse grain and have bad properties. So you heat to non-magnetic, you quench it in oil, and then you temper and it's ready to go. So 8670 is one of the steels that I tested with this method, and the properties turned out very similar to what we had gotten with furnace heat treating. So I recommend this type of heat treating, and I recommend that you go watch my video and read articles on thermal cycling and how to heat treat in a forge. It will tell you exactly what to do for any given low alloy steel on how to heat treat in a forge. It's not my preferred method. I prefer using a furnace where we can get consistent results with the same temperatures every time, and you know what you get every time. There's no screwing it up. But if you're going to heat treat in a forge, at least do it in a way that's going to increase your chances of success. To summarize the heat treatment with a furnace, you should normalize at 1550 to 1600 for 10 to 15 minutes and then air cool. You anneal at 1385 for 30 minutes and slow cool to 1100. I use 300 degrees per hour. and that should work for these steels. You do not need a grain refinement step. The anneal effectively does that. It's a very low temperature process. It's just over critical. The grain is super fine, and then the slow cooling is what gives you your even carbide structure. It's all set up for the final heat treatment, and it's nice and soft for drilling and bandsaw cutting. Then you austenitize by holding for 10 minutes and quenching in oil. For L6 and 8670, because they have a chromium addition, 1500 degrees is the best temperature. For 15 and 20, because it doesn't have chromium, I recommend 1475. Both of those result in awesome toughness like you saw in this article, both for the 8670 and the 15 and 20. Cryo you can do if you want. It is optional. I didn't do it for these tests. You don't need to do it. You don't need to use cryo for any steel if you austenitize it correctly. But with cryo, you can get higher hardness. Then temper twice, 1 to 2 hours each. You got to air cool in between. And then temper between 350 and 400. Higher than 400, you are in danger of getting tempered martensite embrittlement. Lower than 350, and you are in danger of insufficient tempering, as we saw with 15 and 20, where the 300-degree temper was much lower in toughness. So that is a look at nickel steels. I hope you learned some things. There was a lot of details in this, some caveats, some mysteries, but overall I think we can conclude that nickel is a positive element for toughness. These steels are not too hard to heat treat if you follow some basic guidelines. So I'd like to thank my Patreon supporters. So, these studies that I just laid out here, I did a bunch of heat treatments, a bunch of machining, a bunch of testing. That all costs money and a lot of my time. And so I appreciate all the supporters from Patreon that allow me to do these kinds of studies. So if you want to see more studies of these done, please come to patreon.com/knifesteelnerds. So thank you to everybody who has signed up. And if you think about it, or you have some questions, you can email me through my website, knifesteelnerds.com. If you want to learn more about how heat treating works, there were things in this video you didn't understand, let's say. You can buy Knife Engineering. That's my book about how to heat treat and avoid pitfalls with knife design. So that's a good introduction to how heat treating works, how steel works. What are stress risers? You know what a stress riser is? If you don't know what a stress riser is, you got to go buy Knife Engineering so you can learn. So anyway, this was a fun one. So thanks for watching, everybody. Bye-bye.